Cell phones are pretty breakable. I should know, I've broken a couple. We put cases on them to help keep them from breaking when we drop them. Today we're going to think about what are the things that have to go into the design and the engineering of this kind of a case. Instead of dropping cell phones, because that can be kind of expensive, we're going to substitute a cell phone for an egg. So this, of course, is a plastic egg. We'll call it a stunt egg. What we're going to do is you're going to have an actual real egg. Hopefully you've got one at home if you're doing this at home, or I'll supply some at school. And you are going to create some kind of device where you can drop this egg either into a device or surround the egg in a device so that it won't break when it hits the ground. Pretty straightforward. Be sure that if you're doing this at home, you're dropping it on something hard, because we're going to be dropping it on our linoleum floor here in the classroom. So what are the limitations that you have? One of the things engineers always do is they look at the limitations and constraints. You only get 7 sheets of paper and a half a meter of tape. Half a meter is about like that. So with 7 sheets of paper and a half a meter of tape, this egg needs to fall from 1.5 meters. 1.5 meters is about my shoulders, somewhere up in here. You can measure that out at home if you'd like. So, if you're in class, we'll do this together, and we'll drop them and see how this goes. And if you were at home, please video your drop. Be sure you show me taking the egg out so that I can see if it breaks or not. That'll be fun. And there is a worksheet that goes along with this. Please follow along with that. And I'll come back when you're done, and we can actually talk about what you need to know. In order to fully understand an investigation involving the egg drop, we got to understand a term called momentum. Momentum, you've probably heard of this before. We say that something has a lot of momentum, or it's a lot of things when things are colliding. We talk about momentum. Momentum is another way to really discuss the motion of an object. It's known as the mass times the velocity. We give momentum the variable p, lowercase p, as the variable we choose. Now, you might ask, why don't we use a little m? Well, a little m is mass. I have no idea why they chose p, but they did. So momentum is mass times velocity. Now, this might seem a little bit weird because we already have an equation that has just the terms mass and velocity in them. We have kinetic energy is 1/2 mv squared. So you can think of momentum somewhat similar to kinetic energy. When we solve these problems in this chapter, it's going to be a little different than what we did before. We're not going to be looking at free body diagrams and little things like that. We're going to look at the problem holistically. Let's take a look at an example. Okay, let's take a look at this example with this car. We can describe the motion of this car in several different ways. I have a kinematic description of the motion of this car. It's traveling 6 meters per second. It has a mass of 1,100 kilograms. That would be kind of a kinematics. I'm describing the velocity of the car. I can also describe the kinetic energy of the car. We would say that the kinetic energy is 1/2 mv squared, or in this case, 1/2 times 1,100 times 36, which is 19,800 joules. We would say that it has this many joules of energy. But now we can also describe it in terms of its momentum. This car has a momentum, m times v, of 1,100 times 6, which is 6,600 kilogram meters per second. The units for momentum are kilogram meters per second. Kilograms times meters per second. So I can describe the motion of this car in several different ways. I could also put a graph of velocity and time and keep it going at 6 meters per second the entire time. There's lots of different ways I can describe the motion of this car. But let's look at what happens when this thing changes its motion and how we would describe this. Okay, let's take a look at the same car. So the same car ended at 6 meters per second, but 1,100 kilograms gives us 19,800 joules and 6,600 kilogram meters per second in terms of momentum. That's kind of holistic of what's going on. If we look at the beginning here, let's say this car started at rest and then it ended at that. If that's the case, the velocity at the beginning was 0 because it had 0 velocity. It's not moving. Kinetic energy is also 0 because it has 0 velocity. And the momentum is also 0. So how we would figure out in our head, think about how it gets from one place to the other. From here to here, we would say that it accelerated. We would put an A there. There's some kind of an acceleration. And we would do a lot of kinematic stuff. We'd probably need the time or the distance or any of those things that we would have in order to calculate and do some math with that kind of stuff. To get from 0 joules to 19,800 joules, we actually do work. We push force times distance. And so work, of course, is a type of energy, a way in which we do energy, we do work, we gain energy to the system or lose energy to the system if something like friction does work. So work is done. We push force over distance. But what about momentum? To get from 0 momentum to 6,600 momentum, we actually do something called impulse. We put an impulse on the car. Impulse is analogous to work. You can think about doing work actually gives kinetic energy. Doing impulse gives momentum. Let's talk about how that works. Okay, so we have a change in momentum. Oops. We have a change in momentum. That change in momentum is known as an impulse. We have changed the momentum of the system. So what does that mean? Well, we have a mass times our change in velocity. We have changed the velocity. Technically, you could probably change the mass on this if you dropped a weight on it or something like that. But in our case, we changed our velocity. That is an impulse change in momentum. Now, how does this actually work? I'm going to go back to Newton's second law. Okay, because Newton's second law, F equals ma, also has a change in velocity in it as well. It also has a change in velocity. Or actually, if we take A and say instead of A, we have m times our change in velocity over time. Our change in velocity over time is acceleration, so F equals ma. This is actually what Newton kind of talked about in his second law. He didn't really get too deep into acceleration. He talked about changes in momentum, changes in the conservation of momentum, and how those things are done. So let's take a look here. If I say that force is equal to mass times change in velocity over time, I could say that force times time is equal to mass change in velocity. That is impulse. Impulse is force times time. Now, I said it's kind of analogous to work. In work, it's force times distance. It gives you kinetic energy. In momentum, force times time gives you momentum. Let's talk about how this concept relates to your egg drop and how you tried to protect that egg. Chances are there were maybe two things that you tried to do in order to protect this egg. You put cushion or some kind of a fluffy barrier. You took the paper and crumpled it up and made it so that the egg hit something softer than the linoleum floor. Or perhaps you did a parachute. You tried to slow the egg down so it didn't hit quite as hard. So these two things actually involve the idea of impulse. So in impulse, your goal here in the egg is to make the force on the egg as small as possible. You want the tiniest force, that way it won't break. So you want this force to be really small. So what are some things that you can do? If you look at this equation, in order to make this smaller, you could make the time bigger. The time of the impact. If you increase the time of the impact, it will decrease the force. It's kind of like if you hit like this, that's a lot of force, but if you hit like this and increase the time of the impact, that's going to decrease the amount of force. When you catch a baseball, if you ever catch a baseball right in the palm of your hand, like in your glove, it kind of hurts. But if you can catch it in the webbing, or even catch it in the palm of your hand like this, it actually lowers things. This is why we have airbags in cars. You hit the airbag and you slow down over a longer time. That's what the cushion does. This increases the time of impact. So if time goes up, force goes down. So that's one way impulse affects your egg drop. What about the parachute? What are you doing with the parachute? With a parachute, as the thing falls, when it hits the ground, it's not going as fast as without the parachute. So actually what you're doing with the parachute is you're decreasing the change in velocity. When it hits the ground to when it stops, that time of impact, if that's a smaller change in velocity, the force is less. So this decreases the change in velocity. Both of these things are ways in which you can protect your egg. We're going to move on to collisions next time and see if we can't do this with a little bit bigger objects.